Imagine trekking through a prehistoric jungle, 100 million years before humans existed, and stumbling upon a fully functional glass and steel skyscraper. It should not be there. The tools to build it didn't exist yet. We were still using sharpened stones. In early 2026, the James Webb Space Telescope identified a new population of objects. They've been nicknamed Platypus Galaxies. Tiny, compact, and according to everything we know about the birth of the universe, impossible. In our standard model, galaxies grow like trees, slowly, over billions of years, through messy collisions. Small clumps merge into bigger ones. Dwarfs combine into spirals. Spirals grow into giants like the Milky Way. It is hierarchical, predictable, gradual. But these platypuses appear just a few 100 million years after the Big Bang, already fully formed. They are not just oddballs. They are a red flag that our cosmic timeline is fundamentally broken. Because if these skyscrapers exist, then the foundation of cosmology isn't just wobbly, it is missing. To understand why, we need to understand the rules. After the Big Bang, the universe was a glowing fog, hot plasma with no structure. It took 380,000 years just for atoms to form. Then came the cosmic dark ages. No stars, no galaxies, just gravity slowly pulling matter together. Gravity is a patient builder. It works like cosmic Lego. Small pieces first. Dwarf clumps become small galaxies. Small galaxies merge into spirals. Spirals grow into giants. That slow buildup is the backbone of the Lambda CDM model, the framework that includes dark matter as invisible scaffolding, holding everything together. Now imagine finishing the tutorial level of a game and suddenly facing the final boss. That is what Webb is seeing. These platypus galaxies are up to 100 times smaller than the Milky Way. But their stars are mature. Their chemical fingerprints show oxygen, carbon, even iron. Iron is not primordial. It is forged in the cores of massive stars and released only when those stars explode as supernovae. To detect iron this early means entire generations of stars have already lived and died. But we're seeing these systems less than 500 million years after the Big Bang. 500 million years sounds long until you compress the age of the universe into a calendar year. The Milky Way forms in March. Our Sun appears in September. Humans arrive in the final minutes of December 31st. Platypus Galaxies. They are already there on January 1st, fully built. This is the point where the math stops making sense. If you were an astronomer looking at this data, would you trust your telescope, or would you assume the universe is playing a trick on you? If you're finding this mystery as unsettling as the scientists do, hit the like button so the algorithm knows we are digging into the real stuff today. But astronomers do not guess ages, they measure redshift. As the universe expands, light stretches toward red. The farther away something is, the earlier in time we are seeing it. Webb found these objects at redshift 10. That is cosmic infancy. At first glance, platypus galaxies look like simple points of light, like quasars. Normally, a tiny bright dot that far away is a supermassive black hole devouring gas. But then came the spectroscopy. When you split light into its spectrum, it becomes a barcode. Every element leaves a fingerprint. A quasar spectrum looks like broad rolling hills, gas whipping around a black hole at near light speed, smeared by extreme motion. But the Platypus Galaxies do not show broad hills. They show narrow, jagged peaks. That is not a feeding black hole. It is starlight. Hundreds of millions of stars crushed into a region smaller than the central bulge of our own galaxy. In our neighborhood, stars are separated by light years of emptiness. If our sun vanished tonight, the nearest star, Proxima Centauri, would be 4 light years away. In a platypus galaxy, stars are packed up to 1,000 times tighter. If you stood on a planet there would be no true night. The sky wouldn't fade to black. It would glow constantly, like a permanent high noon. This is not just brightness. This is density. And it is the smoking gun. Because density means gravity had to work faster than we thought possible. Gas had to collapse with near-perfect efficiency. Almost every hydrogen atom must have become a star. Nature is rarely that tidy. And then there is the iron, ash of the universe. Iron only appears after massive stars live fast and die violently. Detecting iron at Redshift 10 is like walking into a kitchen built 5 minutes ago and finding cold ashes in the fireplace. Something was burning long before the house was finished. Under lambda CDM, dark matter halos provide the gravitational scaffolding for galaxy formation. Without them, gas cannot collapse fast enough to explain what we're seeing. Yet these systems appear hyper-compact, almost overachievers, forming stars with astonishing efficiency. So we face a choice. Option A. Our star formation models are missing a massive turbo button. Option B. Our redshift measurements are wrong, though multiple confirmations suggest they aren't. Option C. Dark matter behaves differently in the early universe, is the one that keeps cosmologists awake. Because if the early universe was not a slow dawn, but a chaotic construction boom, then we have misunderstood the first chapter of cosmic history, and cosmology is cumulative. Measurements of the cosmic microwave background from missions like Planck spacecraft align beautifully with our expansion models. Until now, platypus galaxies are small, but small anomalies can trigger revolutions. The original platypus baffled biologists because it broke categories. It looked stitched together from different evolutionary branches. These galaxies do the same to physics. Small as dwarfs, dense as giants, chemically mature, but born at the beginning of time. Platypus galaxies should not be there, but they are. When we look deep into space, we are not just observing distant objects, we are stress testing reality itself. And right now, those stress tests are revealing cracks, because somewhere, nearly 13 billion light-years away, entire cities of stars are blazing into existence, far too early. And we may have just discovered that the universe grew up much faster than we ever imagined. But the question remains, did we get the timeline wrong, or is there a force in the early universe we have not named yet?